Hello, everyone, and welcome. My name is Roladid. I'm a senior principal at Geosyntac Consultants in Oakland, California, and the coordinator of the webinar series on behalf of SERDP and ESTCP. I have the pleasure of facilitating today's event. Next slide, please. Go to slide 5, please. This webinar focuses on DoD-funded research efforts to look at treatment technologies for PFAS at sites impacted by AFFF releases in groundwater. We're going to have 3 speakers today, Dr. Erica House from ECT2, Ms. Ree Wang from Cyclopure Inc., and Dr. Kent Sorensen from Alonia. We're going to have a Q&A session after each of the speakers, and depending on how we're doing on time, we're going to conclude with a final Q&A session. The next few slides provide instructions on optimizing your webinar experience. If you have not done so already, please download Zoom at the link shown here and provide it to you in your webinar registration confirmation email. If you cannot download Zoom, you can also view the slides using a compatible internet browser such as Firefox IE or Edge. If you have technical difficulties or if your screen freezes, try keying in Control and F5 to perform a hard refresh of your browser. And in case of continued difficulties, you can download a PDF of the slides from the webinar webpage and call into the conference line provided to you in your webinar registration confirmation email. Another viewing option is to tune in to the SERDP and ESTCP YouTube channel, as we will be live streaming the webinar at the link shown here. Just a few reminders, today's broadcast will be listen only. You may submit your questions by using the Q&A box on your screen. You do not need to wait until the Q&A sessions to submit your question. We do encourage you to get them in as soon as you come up with your questions. And when you do submit them, please add your organization name at the end of your question so that we can identify you. Please do not submit questions in the chat box. The chat box should be reserved for comments related to technical difficulties. With that, I would like to introduce Dr. Andrea Leeson, who is the Director of SERDP and ESTCP, as well as the Program Manager for the Environmental Restoration Program area. Dr. Leeson has been with SERDP and ESTCP since 2001, and before that, she served as a research leader at Biddle, where she conducted scientific research on in situ bioremediation and the design and implementation of innovative biological, chemical, and physical treatment technologies for site remediation and industrial wastewater. Andrea received her doctoral degree in environmental engineering from the Johns Hopkins University. Andrea, please proceed.
Thank you so much, Rula, and thanks to everyone who's joined us today for this webinar. Slide 10, please. Before we jump into the webinar, I'd like to talk a little bit about who we are, although I will quickly move through this so that you can get to hear the presentations that you're really here for. We are composed of 2 companion programs. We have SERDP, the Strategic Environmental Research and Development Program, and ESTCP, the Environmental Security Technology Certification Program. And the projects you'll hear from today were selected under the ESTCP area. The SERDP is really a traditional R&D program, research and development program. And what we're looking to do under SERDP is fund research to pursue solutions that will reduce the cost, the risks, and the time required to tackle and resolve installation challenges while always keeping in mind to advance military readiness. Under ESTCP, what we do is we take the technologies and the knowledge that's developed under SERDP, and as it matures, we like to move it into ESTCP, where we can further demonstrate and validate those technologies at military installations. And that way, we can collect the sort of cost and performance information we need for technology transition and broader adoption of those technologies. Slide 11. So these programs are truly delivering tremendous value to the military installations. I will show you in a minute here that we have a number of program areas that we focus on, all geared towards enhancing mission readiness, safeguarding built and natural infrastructure on the installations, ensuring health and safety, looking at cost savings and time savings, and bolstering chemical and material resilience. Slide 12, please. And so we're doing this through 6 program areas that support these mission critical DoD priorities. We have environmental restoration, and of course the projects you'll see today fall under this program area. And right now, environmental restoration has really been tackling the PFAS issue, although we do address other chemicals of concern. We have resource conservation, which is looking at protection of the natural infrastructure on our testing and training ranges. Weapons systems and platforms, that's looking at critical systems and platforms that protect our DoD personnel by dealing with chemicals of concerns that are in various products that have to be used on installations. Slide 13, please. Installation energy and water, which is dealing with the resilience against disruptions to the public energy and water infrastructure. Natural hazards adaptation, of course, identifying and assessing natural hazards that threaten DoD installation infrastructure. And then finally, munitions response, which it's dealing with the UXO issue across active installations, as well as formerly used defense sites or FUDs. Slide 14, please. SERDP and ESTCP combined work with hundreds of federal, university, and industry R&D partnerships. And I really encourage you to sign up for our listserv shown here on the link. On that listserv, you will get information about funding opportunities, webinars, and other critical information that's coming out of the program. Next slide, please. So in this slide, for those of you interested in PFAS, and of course you wouldn't be here if you weren't, you will find on our website a graphic similar to this that is interactive, that is showing you the history of what SERDP and ESTCP have funded over the years in the realm of PFAS in the environment, starting from 2011 through till this day. We'll drop the link in the chat room that will take you to this page so you can find it yourself. But in this page, you'll be able to you'll click on one of these boxes for a particular topic you're interested in, and the boxes above the timeline represent SERDP efforts, below are ESTCP efforts. Click on one box. It will take you to the information about that topic that we were looking at that in that particular year. It will list the projects that were selected under that topic. And then each of those topics or projects that are listed, that will also be linked. And you can move through to an individual project webpage that will provide you the information that we have on the project. There's a brief summary there. There's contact information for the lead investigator. And once public documents are available, they're posted to that website. So there's a tremendous amount of information available at this slide. Slide 16, please. So today what I'd like to talk about is the ESTCP PFAS treatment testbed projects that we've been conducting. You'll see highlighted in the middle are the group of projects that we'll be presenting today. But what we did with these testbed projects is that we had 3 goals in mind. What we wanted to do is move promising technologies, and these were technologies that were developed under ESTCP or outside the program, and we wanted to move those to commercialization. We also wanted to have a head-to-head comparison of different technologies at each of these individual test beds, and then potentially streamline the future procurement of successful technologies. So the other 3 test beds we looked at, there was one at Joint Base Elmendorf-Richardson in Alaska, or JBEAR, that was looking at ex situ soil treatment projects. We had a cohort of projects that's looking at ex situ concentrate destruction operating in Michigan and North Carolina, and these projects were taking the residuals from the separation projects that you'll hear about today and doing further destruction on those. And then we have another cohort of projects that's dealing with ex situ sediment treatment projects where they're looking at the sediments from ponds at both Schriever and Peterson's Space Force Base in Colorado. And so we'll hear from those projects as well later next year. And then the cohort we'll be talking about today is doing the ex situ water separation at Formal Naval Air Station at Willow Grove, Pennsylvania, and Biddle Air National Guard Base in Pennsylvania. I did want to say that certainly these big demonstrations are simply not possible without the support from the installation. And I know I speak for everyone on the call today, as well as within the program office, that we absolutely cannot say enough about the support we received from the Willow Grove and the Biddle Navy personnel. They were instrumental in making these projects successful. So I'd like to specifically thank Jason Spiker, Jim Rue, and Lee DePersia from the installations for helping make these successful. Slide 17. I did want to end my remarks with guiding you to the link for the webinars. We have been doing webinars for several years now. Every one that we have done has been archived, so you can always go back to see webinars that you may have missed. And you will see future webinars, and you can sign up for those webinars at this time as well. So I hope to see you at future webinars. Slide 18. And I will turn this back over to Rula. Thank you, Rula.
Thanks, Andrea. It is now my pleasure to introduce today's first speaker, Dr. Erica Houts, who is a technical director at ECT2, where she evaluates and develops treatment and destruction technologies that can be incorporated into ECT2 treatment systems. Erica also has extensive experience in developing analytical and experimental methods for the measurement and breakdown of anthropogenic compounds in environmental and human samples, including developing the top assay for PFAS measurement. Erica has served as a PI or co-PI on ESTCP projects and has also worked on environmental remediation projects for the Air Force, Navy, and Army. She earned her bachelor's degree in chemical engineering from Ohio State University and master's and doctoral degrees in environmental engineering from the University of California at Berkeley. Erica, we're delighted to have you. Please start with your presentation.
Great, thank you, Rula. I'm happy to be here today and really excited to share the results of this project. We wrapped it up sort of recently, back in March, so eager to talk about it with you guys. So just to go over what we'll be discussing today, I'm going to do a brief overview of regenerable ion exchange treatment for PFAS. I'm going to overview the demonstration in terms of site characteristics and groundwater characteristics that we were treating, go over some of the equipment and site images so you guys can really get a sense of our equipment and what the different processes look like. I'll be discussing performance data on both the groundwater treatment and the regeneration, and go over some key results, conclude, and then discuss benefits to the DoD. So as we talk about regenerable ion exchange, we're basically talking about a three-part process. The first, many of you may be more familiar with, that's ion exchange water treatment for PFAS. We use an anionic exchange treatment media or multiple kinds of anionic exchange treatment medias. They have a dual attraction mechanism for PFAS, both a hydrophobic attraction mechanism and an ionic attraction mechanism that absorb anionic PFAS from impacted water and fixed media beds. And then the more specific parts of this process that we were demonstrating were the regeneration of that media. So that's where we take an organic solvent and a counter ion and break that attraction between the PFAS and the media in order to replenish the media so that it can be continually reused for more groundwater treatment. And then we take that spent regenerant solution and we distill it in order to recover the solvent so that we can continue to use that in future regeneration cycles. It's a sustainable aspect of this process. And then importantly for these projects, we're left with a product called a still bottom, which contains all of the PFAS that were first adsorbed onto the resin and then desorbed from the regeneration process. And it's in a salty aqueous matrix that can then be used for PFAS destruction emitters. So as was mentioned, we were demonstrating at the former Naval Air Station Joint Reserve Base Willow Grove, which is about 45 miles outside of Philadelphia. We were operating at a source area where there was likely historical AFFF releases associated with a building fire suppression system. This was a pretty highly impacted source area. There have been multiple demonstration projects that have occurred here, and they've been pumping groundwater for a while, and there's still relatively high levels of PFAS. I'll get into that a little more in the next slide. We were treating at a flow rate of 9 gallons per minute, and we were on site for about eight months of operations from June 2024 until this past February. And over that time, we treated 2.5 million gallons of groundwater. So the images that I'm showing on the right are the placement of our treatment systems. They're both containerized, they both ship on a flatbed truck. On the in the background, the treatment container that has less equipment outside of it, that's where we contain our anion exchange groundwater treatment equipment. And then in the foreground is our regeneration equipment. When it ships, all of that equipment is inside, and then some of the components get placed outside in secondary containment. So in terms of the source water, fairly high PFAS, about 50 micrograms per liter total PFAS, 80% of which was PFAS. It kind of varied over the demonstration period, but these are our average values detected in the influent. Apart from the PFAS, there was not a lot of other constituents in the groundwater that posed any pretreatment needs at the site. Pretty low total organic carbon, about 1 milligram per liter, pretty low chloride. Not a lot of calcium and magnesium, so no real issues around scale formation, and also very low iron. So the only pretreatment that we brought to site was a mixed media filtration and bag filters to help remove any solid particles. This is a simplified block flow diagram of what we did. Our influent contained, as we just went over, 50 micrograms per liter target PFAS, went through a 3-part regenerable ion exchange vessel that was sort of a simulated lead vessel. Then it went through a polished ion exchange vessel, and we ended up with treated water that contained nanogram per liter levels of our target PFAS. So our targets, we had 2 different targets as we operated. The first one was drinking water MCLs. So that would be 4 nanograms per liter PFAS, PFOA. At the time, there were also some limits on PFHXS, PFPS, GenX, and PFNA. So we were non-detect on all of those compounds. And then there were also treatment targets that we wanted to hit for short chains, which was 1/10 of the tap water RSL for PFBA and PFHXA. We had various sampling points along that flow path. We regularly sampled our influent and the various midpoints of the treatment vessels and the effluent of those vessels. And then when we started to see breakthrough of our target compounds at a midpoint vessel, we would remove all 3 of those vessels, regenerate them in series as a unit with our regeneration solution, which contained methanol, water, and sodium chloride. And then we would distill that solution in batches. And we would end up with aqueous still bottoms that contained about 500 milligrams per liter total PFAS. So this is kind of the essence of the separation and concentration process. These are some images of our treatment system interiors. On the left side is our regenerable ion exchange system. There's various tanks for utilization tanks for storing influent and treated water. Our regenerable vessels are these 3 black vessels here. They can be unclipped and taken into our regen container, which is displayed on the right. In the back there, that is our distillation unit. And there's another, half of the container where we would put the actual vessels. In terms of the regeneration process, we disconnect the regenerable vessels. We move them into the regen container. You can see them clipped in back here. We connect them to the regen system, piping via camlock fittings, and then we regenerate those vessels in countercurrent flow, first with a brine solution, then with a methanol brine solution, and finally we rinse them to remove any of that residual regenerant solution. And so you can see on the bottom images of those various solutions as they exit our vessels. So the clear ones that start At the top left are the brine soak coming out. When you start introducing reagent solution, you start to pull off natural organic matter out of the vessels that had also absorbed to the resin. So that's why it's kind of a brown color there. And then as the regeneration solution passes through, you get lighter and lighter solution as all of that NOM is removed, and concluding with clear solution as you move through the rinse process. So these are not analytical samples; they were just used for visual purposes and also some physical measurements. So each of those spent solutions is stored in separate tanks for further processing. And then with the distillation process, we take that spent regenerant solution. We also include the first couple fractions of our rinse water, which are also relatively high in solvent, and then we distill them. And then the distillate is purified with ion exchange media within our regen container to remove any carryover PFAS. There's usually not very much carryover PFAS, but we do sometimes see carryover of the more volatile types of PFAS and some of our higher concentration constituents. So then we store that purified methanol for the next regeneration process. And then we're left with the still bottoms. So over our 8-month demonstration period, we did 3 treatment cycles. None of them actually hit full breakthrough of any of the MCL PFAS. We stopped the first cycle at about 23,000 bed volumes. This was in order to demonstrate three cycles of groundwater treatment and regeneration. But so we estimate it would take about 30,000 bed volumes before we would see PFOA breakthrough. We did clearly see PFBA breakthrough above its treatment target of 1/10 of the RSL at about 7,500 bed volumes. And then I'm showing breakthrough values for some of the other compounds over here. I would say the takeaway is that, we can treat any of these compounds. The trade-off is that if you are trying to treat for really mobile compounds or compounds that don't absorb as well, you're going to be on a faster regeneration cadence, or if you were replacing media, a faster replacement cadence. So the time between regeneration events effectively just depends on what is your treatment goal. And so even though this water was very PFOS dominant and generally perfluoroalkyl sulfonate dominant, PFOS still was the first constituent that drove breakthrough out of the MCL compounds in these treatment vessels. And so I'm showing breakthrough curves of PFOA here out of our 3 different regen vessels over all 3 cycles. So this is the first third, RIX1 is the blue lines, and then the pink and the orange are the second and third vessels. The pink and the orange are all pretty close to 0 because we really didn't have many detections in those portions of the vessels. But the point is that all of these curves overlap very nicely. There's some fluctuations just due to changes that we had in flow rate and influent concentration, but that just suggests that the regeneration process was very effective at returning media to its original condition and seeing a repeatable breakthrough curve. This is a little easier to see with PFBA since we had a more clear breakthrough of this compound. Again, the blue lines are the RIX1, our first regenerable vessel, the orange one is the second, and the pink one is the third. And so over all 3 of these cycles, we saw very overlapping breakthrough curves. And you can also clearly see where we hit that breakthrough across that treatment threshold at around 7,500 bed volumes for PFBA. Here I'm showing our vessel effluent concentrations in terms of total PFAS over all 3 of our loading cycles. The first one was the longest and the second 2 were shorter so that we could meet, kind of competing goals of this demonstration. What you can see is that the media capacity is fully restored after each regeneration event, where once we start monitoring our treated water effluent, again, it goes back to 0. And particularly the orange line, which is the third regen vessel, that's really kind of our effluent out of our regen vessels, remains very, very low relative to the influent throughout the entire treatment duration. Another thing we were really interested in understanding with this data, or rather depicting, is that we get good recovery of the PFAS that we absorb in our regenerant solution. And so what I'm displaying here is a PFAS mass balance on our first regeneration event. Please note this is a log scale. And we're looking at PFAS mass in different fractions. So the first fraction, the dark blue one on the left, is the PFAS mass we estimated that we captured based on our influent measurements and our volume that we treated. The green bar is the PFAS mass in our spent regenerant solution. So that would be all of the PFAS that we absorbed into that solution. And you can see that those two bars are really, really close for all of these analytes. That's really good. That means that we fully recovered all of our PFAS that were absorbed to the media. We also had maybe 0.1 to 1% of our PFAS in the spent brine tank, and then even less than that in our rinse water. And so that just confirms that the regeneration process was very effective, and that it all pretty much ended up within the regen solution. I should say that both the rinse water and the spent brine water are further treated through our groundwater treatment system before discharge. So any of that small residual is treated. What we're left with is the still bottoms material. We had around 500 milligrams per liter total PFAS in these samples, PFAS being our predominant constituent, just as it was in the influent. Overall, we had about a 20,000 concentration factor. From if we treated 20,000 gallons of groundwater, we ended up with about 1 gallon of this waste residual. It is very high in chloride and has a pretty significant chemical oxygen demand. I just note this because that can impact some of the destruction vendors. So just to conclude, this was a prototype demonstration in terms of a more automated mobile regeneration system. But in general, this is a very mature, fully commercial technology. We have installations up to 8,000 gallons per minute of this technology. We've seen that the treatment media is really robust and that we can return it to optimal virgin operating conditions after multiple regeneration cycles. In this one, we just did 3 over an 8-month period, but we have systems where we have 5 or more years of media lifetime, where we've seen no degradation in the treatment media at continuous full-scale systems. We get a very high waste concentration factor from the water treated to the still bottoms. Here we observed one of about 20,000. We have other processes by which we can concentrate this further. We can load the still bottoms onto media called superloading to get as much as 1 million-fold waste concentration factor, or we can take those still bottoms and deliver them to a PFAS destruction technology that takes an aqueous waste. So where we see the benefits of this process to the DoD is that you can get very effective and reliable water treatment to low-level or non-detect PFAS criteria for really all anionic PFAS. As I mentioned, if you're going to treat shorter compounds, you're going to have a more frequent regeneration cadence. There's a lot of waste reduction associated with this process. You will eliminate at least one major waste stream, your routine spent media. There may be pre-treatment media waste depending on what the process is, but the actual PFAS treatment process will no longer have a waste stream associated with it. We know that this pairs well with PFAS destruction technologies. The specific material from this project is going to multiple vendors, including hydrothermal alkaline treatment and SQO. We've also done work with other technologies, electrochemical oxidation, UV reduction, plasma, fair bit of work with HALT, that we know these technologies can work in this media. And it is a very high concentration, low volume waste where they can operate more efficiently. In terms of applications that are ideal for regenerable systems, there is an upfront cost associated with the regenerable media, where we see payback and overall life cycle cost benefit is when we have high influent concentrations. This would be an example of a site where we have a higher influent concentration where a regenerable product would make more sense. When you have medium to high flow rates where you're really going through a lot of treatment media, or when your treatment goals include removal of short chain or even ultra short chain PFAS. Essentially, all of these applications share something in common, which is that they have a high media exhaustion rate, and that is where regeneration makes economic sense. Additionally, you can have a single regeneration system service multiple resin systems and get some economy of scale out of your regeneration system. So I wanted to briefly acknowledge the Defense Innovation Unit for the funding, as well as ESTCP Really want to thank Jason Spiker at NAVFAC, who was instrumental to this project being successful, super communicative, and really helped us go through all the logistics of this project. And there's a lot of people at ECT2 who contributed to this project. I listed a lot of the major players alphabetically here. This was definitely a team effort at ECT2, and I'm really grateful to all my colleagues for all the support. Thank you.
Thank you so much, Erica. Just a reminder for our audience, please submit your questions using the Q&A box on your screen. We have received several questions for you, Erica, and I'm going to start with the first one that was submitted by the Air Force Civil Engineer Center. If the RSL is by definition a concentration below which there is no acceptable risk, why was the target performance at 1/10 of the RCL?
That was something that we decided on in collaboration with the ESTCP technical committee.
Great, thank you. And a follow-on question also from AFGAC. Did the project come up with an estimate for cost per gallon at the configuration and scale that you use?
We will have a cost analysis within our final report. And I believe, I don't know if we're going to express it quite in that format, a cost per gallon, but we will have life cycle costs and O&M costs for different scales of systems, including one of this size.
Great. And,
so,
and,
yeah.
And will that report be available, Erica?
So I think it will be available pretty soon. I would say within the next 3 months. We have a 99% complete draft right now. There'll be a review phase, but I think it will be pretty soon.
Great. And as a reminder to everyone, if you click at the link for Erica's project, ER 238391, that's where you can download a free copy of the final report that Erica mentioned. All right, the next question is from the University of Utah. If detergents such as SDS are also present in the water, 2 questions. Does that impact performance? And does the resin also capture the detergents in addition to the PFAS?
Yeah, that's an interesting question. Probably we would have upfront pretreatment if we had a water that contained those kinds of detergents. We might even employ some kind of other advanced oxidation-based pretreatment process ahead. We like to target a pretty low TOC going into the resins. So usually we would have pretreatment for that.
Great, thank you so much. And a follow-on question also from the University of Utah. What was your reason for selecting methanol instead of ethanol for regenerating the resin?
So we do have some sites where we use ethanol. There are certain benefits in terms of solubility of PFAS and the amount of sodium chloride we can dissolve into methanol, some operational benefits, but we have systems that run on alternative solvents as well.
Great, thank you so much. This is a question from the Utah Department of Environmental Quality, the Division of Water Quality. What was the empty bed contact time in your reactor? Can you re-mention that, please?
Mm-hmm. We had 2.3 minutes per vessel. It was probably kind of overkill. We would probably go more like, 4 to 5 going forward, but we wanted to have a longer empty bed contact time on this demonstration since we split it into 3.
Wonderful. All right. This next question has to do with the types of destruction technologies that are best as a follow-on to the ECT2 technology. Have you tested any of them? Do you have any that are currently working right now that you can talk about?
Mm-hmm. So there's a number of, publications of us pairing various technologies. I think notably HALT pairs very nicely with still bottoms because there's a high compatibility with salt, and there's good broad spectrum destruction. We've also had good results pairing with electrochemical oxidation, some types of electrodes at least. We've got a demonstration with plasma and a few with UV reduction. To date, we haven't done much work with SQO because typically SQO and salt are not super compatible, or high salt rather. But be interested to see how the destruction vendors perform. There's 3 different SQO vendors that will be treating these materials. And so we'll have a little more information on SQO performance with still bottoms at the conclusion of these testbed projects.
We may have lost Rula. This is Dr. Tsukumo Geosyntek. I'm her collaborator on the webinar series. I think we can now probably move on to our second speaker. So I'll go ahead and introduce them. Give me one quick moment.
Okay, I thought I might have gotten disconnected, so that's good to hear.
Slide 38. Okay. No worries. I'm going to go ahead and introduce our second speaker. It is Miss Ri Wang, who's Vice President of Environmental Engineering at CyclePure in Evanston, where she leads the design and development of engineered system applications using DexOrb for PFAS removal in diverse water matrices. To date, Ri has worked on over 40 pilot and full-scale DexOrb systems and has played a key role in several PFAS projects funded by the Air Force and ESTCP. Her technical background extends to lab-scale PFAS treatment modeling and design, pilot system development, and full-scale system design. She earned her master's degree in environmental engineering from Cornell University. With that, I'll turn it over to you, Ri.
Thank you for the introduction, Eric. And welcome everyone for joining this webinar. So during this presentation, I'll be discussing our project on efficient PFAS removal and concentration by high-capacity cyclodextrin adsorbent DexOrb for the use in groundwater remediation. Again, this project is funded by ESTCP in partnership with the Defense Innovation Unit and great support from the Navy. Okay, so in this presentation, I will provide an overview of the DexOrb technology, as well as our ESTCP project scope, pilot system design, and our key findings from this demonstration. I'll discuss the PFAS removal performance using the first production DexOrb media, as well as the regenerated DexOrb media performance, and also introduce the results on DexOrb regeneration for PFAS desorption and concentration. I'll conclude the presentation with a summary of the key results and the benefits to the Department of Defense. So what is DexOrb? So DexOrb is a beta-cyclodextrin-based adsorbent engineered for removing PFAS from water environments through hydrophobic interactions. DexOrb is synthesized through a single-step polymerization reaction to make the soluble beta-cyclodextrin to insoluble format, so it can be applied into water filtration applications. So the uniqueness about cyclodextrin is that it has this uniform cavity size of less than 1 nanometer, and that is perfectly for capturing PFAS and other organic micropollutants in the Dalton size of 150 to 1,000. Unlike traditional adsorbents such as granular active carbon, GAC, GAC also removes PFAS by hydrophobic interaction, but it has uneven pore size. So by the virtue of the uniform cavity size in Dexorb is not susceptible to computation from the other constituents in the water matrix, such as POC and other inorganic ions. Other great features of Dexorb includes rapid kinetics, which translates to shorter empty bag contact time and higher absorption capacity because of the availabilities of the cavities for PFAS removal and uptake. Another thing we always highlight is that it's important to note that Dexorb is not an ion exchange resin. The removal performance is based on the post-gas complexation between the cyclodextrin cavities in Dexorb and the PFAS molecules in water matrix. And that's a hydrophobic interaction. So for the Dexorb, it's synthesized as powder format and further granulated to enable the flow-through hydraulics. So Dexorb granules has NSF 61 certification, and it is approved for drinking water use by both Massachusetts Department of Environmental Protection as well as New Jersey Department of Environmental Protection. And Dexorb are being actively used in both drinking water and non-drinking water applications. Currently, Dexorb is manufactured at industrial scale, and you can see the image on the right-hand side that's showing the granules in a commercial product format. Okay, so in this slide, these two illustrations further highlights the mechanism of the molecular selectivity of Dexorb. So Dexorb's cavity fits very well with PFAS molecules, as I mentioned before. And at the same time, Dexorb excludes the larger molecules such as natural organic matter. Those are too large to fit into the cavity. And for inorganic ions, those are too small and too hydrophilic to bind with the Dexorb cavities. So this size exclusion mechanism enhances the selectivity of Dexorb, and it helps maintain the consistent great performance across different water environments while using Dexorb. So with those superior features, Dexorb are applied in both drinking water and non-drinking water applications. In drinking water, we treat surface water, groundwater, as well as our concentrate generated at a drinking water treatment plant. For non-drinking water applications, we treat groundwater at military sites like this ESTCP project, closed landfill. We treat wastewater from both industrial metal plating as well as municipal, and we also treat landfill leachate from different landfill sites. So this slide demonstrates the process of using Dexorb. So after the field treatment operation, our backend process, we take the spent media back into our centralized media regeneration facility, where we load the spent media into vessels and perform a backwash operation with the regeneration solution, which is a mixture of ethanol and water. Through this process, the media is fully regenerated, and then for the spent regeneration solution, it is further concentrated down to steel bottom waste using distillation. At the same time, the ethanol in the regeneration solution is recycled for future use of regeneration. So this waste handling for PFAS concentration, it is a very efficient process that's unique to Dexorb adsorbent. The small volume of the PFAS concentrate waste can be efficiently destroyed by PFAS destruction technologies. Okay, so for this ESTCP demonstration, the overarching goal is to demonstrate the Dexorb packed bed filtration system in the pump and treat remediation of the AFFF impacted groundwater in Willow Grove, Pennsylvania. It's the same site as Erica just presented. We have three major technical objectives for this project. The first one is to demonstrate the effectiveness of the first production Dexor media to remove PFAS. Second objective is to demonstrate the spent Dexor regeneration in a backwash operation to achieve PFAS desorption and concentration. And the third objective is to demonstrate that the regenerated Dexor media has the same great PFAS removal efficiency. Okay, so on the right-hand side, you can see the picture of the installed Dexorb packed bed filtration system at the site in a weatherproof container. The system has two 14-inch diameter fiberglass reinforced vessels in lead and lag configuration. The pilot system operates at a flow rate of 2 gallons per minute continuously with a hydraulic loading rate of 1.9 gallons per minute per square foot. Each vessel is packed with 120 pounds of Dexor granules to provide an empty bed contact time of 15 minutes. This slide shows the process flow diagram of the pilot system. So in the system, we incorporated the pressure meter, flow meter, and flow totalizer to monitor like the system pressure drops, flow rate, and flow throughput. We also have 3 sampling ports to collect PFAS and other general water quality samples at the influent SP1, effluent SP2, mid-fluent SP2, and then the system effluent SP3. Okay, so let's talk about some of the PFAS removal performance for the first production Dexor media. So for this pilot, it is receiving the groundwater at an average total PFAS concentration of around 28,000 ppt. Our target PFAS for this project is the previous US EPA MCL PFAS 6, which includes PFOA, PFOS, PFBS, PFHXS, PFNA, and GenX. GenX was not detected in this water, so the total concentration for our target PFAS was around 24,000 ppt, and PFOS is the most concentrated one. Its concentration is over 18,000 ppt. So during the first phase of the project, the Dexor pilot operated continuously for 4 months, treated about 323,000 gallons of groundwater. That translates to 11,000 bed volumes. During the 4 months, minimal pressure drop across the system was observed, and along with a stable flow rate. So that shows the really smooth and robust system operation. For the PFAS performance, all our target PFAS was removed to non-detect levels at the lead vessel effluent or the mid-fluent, and the PFAS, the previous PFAS hazard index was reduced from 300.01 to 0. For the total PFAS, it had larger than 97% removal throughout the 4-month pilot operation period. In addition to the PFAS characterization, we also included top assay analysis to demonstrate that all the target PFAS precursors were also removed by Dexorb to non-detect levels at the lead vessel effluent, as presented in the bar plot on the left-hand side. On the right-hand side, you can see the general water quality characterization table that shows the parameters at SP1 influent, SP2 midfluent, and SP3 system effluent. So it really demonstrates that, for example, TOC and TDS remained constant before and after Dexorb treatment. So that is confirming the molecular selectivity of Dexorb technology while it's removing PFAS, it doesn't really impact the overall water quality. So after the 4 months of pilot operation, we mobilized the lead DexWork vessel offsite for regeneration. During the regeneration process, as introduced previously, we used the ethanol water-based regeneration solution to backwash the spent media to desorb PFAS, and we analyzed the PFAS concentration in the spent regeneration solution to confirm the PFAS recovery using mass balance by comparing the absorbed PFAS mass in the previous 4 months and the desorbed PFAS mass during the regeneration process. And we used about 100 gallons of the solution per round, and we did 15 rounds in total to evaluate the performance recovery comprehensively. So this slide shows the PFAS recovery of DexWork regeneration. So using the mass balance analysis, we confirmed full PFOA and PFOS recovery of 100%. The final regeneration waste, we further concentrate that down to 300 gallons for delivery to the destruction vendors for their testing. It contains 21 ppm of PFOS and 1.6 ppm of PFOA. And following the regeneration, the regenerated DexWork was reinstalled on site to validate its PFAS removal in groundwater remediation. So for the regenerated DexWork, it's operated on site for additional 3.5 months. It treated 310,000 gallons of groundwater, which is about 10,000 barrel volumes. And consistent with the first production DexWork media performance, it had a smooth and stable operation over the 3.5 months by the stable flow rate and low pressure drop across the system. For PFAS performance, all the target PFAS was removed to less than 2 nanograms per liter at this regenerated vessel effluent. And the hazard index was also reduced to 0. And for the EPA 1633 total PFAS, which includes 40 analytes, we had larger than 98% removal throughout the whole 3.5 months operation period. And for top assay, all the precursors are shown to be removed to non-detect levels by the regenerated DexWork. And for general water quality, it's also confirmed using the regenerated DexWork. The TDS and TOC level, for example, remained constant before and after the treatment. So again, to compare the PFAS removal performance of first production and regenerated DexWork more directly, you can see this bar plot on this slide. So in summary, all the target PFAS are removed to non-detect by the end of the pilot operation, which is 4 months for the first production media, about 11,000 barrel volumes, and 3.5 months with regenerated media for about 10,000 barrel volumes. We could test it longer, but due to like the timeline, so we only run for 4 months for first production and 3.5 months for the regenerated media. And the blue and green tables shows the influent concentration for those two media at those 2 bed volumes. So to summarize, this project validated the PFAS treatment efficiency using DexWork. It can remove the all regulatory PFAS from very high concentration of 24,000 ppt to non-detect levels. And this is achieved using a 15-minute EBCT. At full scale, it will provide a very compact system design with smooth hydraulic operation and low operation and maintenance efforts. Secondly, from the PFAS waste concentration perspective, we demonstrated full recovery of the PFAS from the spent media. And at full-scale operation, we can achieve a high concentration factor of 40,000 for groundwater remediation applications. Certainly, for the media regeneration perspective, the regenerated Dexorb had the equal performance to the first production Dexorb that enables us to reuse the media for multiple cycles, which provides cost-effective and sustainable solution. That leads to the last slide. So this project offers multiple benefits to the Department of Defense. So firstly, the Dexorb system provides a single-step and compact system with high treatment capacity for DoD site remediation. Secondly, the regenerability of Dexorb with full PFAS recovery enables the efficient backend processing for PFAS concentration and the subsequent PFAS destruction. So the DoD can use Dexorb system to treat groundwater with high PFAS levels, as well as other high PFAS concentration water matrices. It can be HFF rinsed, or some wastewater, or some landfill leachate. So lastly, I would like to point you to our project's website and my contact information. So if you have any questions or would like to discuss Dexorb or the project further, please feel free to reach out. And thank you for your attention, and I'm happy to take any questions.
Thank you, Ree. We have received a number of questions. The first one is from Esri Consulting. Have you quantified partitioning coefficients for Dexorb, and are they available somewhere?
Yeah, so we have done multiple different studies. So we have done the most traditional theoretical isotherm study, and that was published in the book chapter of Forever Chemicals that I can send along after this call. And then we have also evaluated using RCCT or column test, which is more providing you operating capacity rather than theoretical capacity using the Dexorb absorbent. So we have those information evaluated at a more scientific, a more clean background, as well as at a more practical using different real water matrices.
Great, thank you so much. Can you explain why the influent and effluent values for TOC and TDS remained unchanged? You talked about that on one of your slides.
Yes. So in this water, we had a relatively low TOC level. It's less than 1 milligrams per liter. For TDS, it's about 200 to 300 milligrams per liter. So we want to have that table to demonstrate that they are unchanged. It's because, as I introduced earlier, for the Dexorb absorption, it has this mechanism is because the cyclodextrin cavities binding with PFAS molecules, while for the TOC, which generally is largely natural organic matters, those molecules are too large, so they cannot fit into the cyclodextrin cavities in Dexorb. And for TDS, it represents inorganic ions, and those are too hydrophilic and too small that will not bind with the cyclodextrin cavity. So that's really to show that the size exclusion effect from Dexorb in a more empirical perspective, and that table demonstrated that.
Great, thank you. This next question is from the Navy, NAFAC XWIC. Has Dexorb been evaluated for treating groundwater with low concentrations of PFAS?
Yes. So for low concentration groundwater, the most common application for us is actually treating drinking water that is groundwater source. We have multiple pilots study on that. We have one in Maryland that's been running for 2 months, we collected, 2 years, we collected lots of valuable data. It's like we had a 5-minute EBCT design there, and we still didn't get the regulatory PFAS breakthrough after operating for 2 months. And we had some other groundwater drinking water pilots in Nevada and other states in the United States. Yeah, so we have those studies on hand that's for a low concentration groundwater applications.
Thank you so much. Can you talk a little bit about the costs associated with using Dexorb media?
Yes. So the Dexorb system, different from other technologies, is that it offers a very simple system setup and solution. So the cost of implementing a Dexorb system will be more about just like procuring the vessel for holding the media and then the media itself. On the operation and maintenance side, it's low operation and maintenance costs as demonstrated in this project. Like the pressure and flow rate are really stable, so you don't need to do let's say backwash, or you don't need to have an intensive energy input. You don't need to have like the operator on site like 24/7. You can basically just have the system set up there, have the flow being pumped through the system, and more like check in every week. And so it's a really simple solution, but effective. So that brings the cost benefits to our clients. And for the spent Dexorb material, our business model is we will take the spent media back to our regeneration facility. So we will perform the regeneration process on the back end. So the clients will just be facing the fresh media loading and spent media replacement.
Great, thank you so much. We have time for two other very quick questions. The first one has to do with the material. Does it use any fluorinated linkers?
So for the Dexorb, it is synthesized through polymerization process. The monomer, the key monomer we use is cyclodextrin. That's where all those great properties of Dexorb derived from. And of course, we need a cross-linker that cross-links all the cyclodextrins together to make it insoluble in water. So our chemistry team, we actually have multiple different versions of Dexorb that use different cross-linkers, and our chemistry R&D team are like continuously evaluating the most cost-effective and best performing cross-linker and polymerization process. So in our suite of the Dexorb different form factors, I think we have one cross-linker that contains fluorine, but it's not a PFAS compound. It's just a small molecule compound that we use to cross-linking the cyclodextrins. But that's among, we have different cross-linker options, and this is patented. So I think it's detailed in the patent information.
Great, thank you for the really good response. We're gonna save the remaining questions actually till the end of the webinar. So we can go ahead and thank you at this point, ask you to stay on the line, but we're gonna go ahead and move to our third and last presentation, which will be given by Dr. Kent Sorensen. Kent is the Chief Technology Officer at Elonia in Boston. He has over 30 years of experience addressing environmental challenges in contaminant treatment and mineral processing across North America, Europe, Asia, and Australia. Kent's work has earned numerous awards, including the 2020 Henry L. Michel Award from the American Society of Civil Engineers for Industry Advancement of Research. Kent has a bachelor's degree in mechanical engineering from Tulane University a master's degree in civil and environmental engineering from MIT, and a doctoral degree in civil and environmental engineering from the University of Idaho. Kent, go ahead, please.
All right. Thank you so much, Rula. Welcome, everybody. Thanks for joining us for this webinar. I'm really excited to have the opportunity to share with you about our surface active foam fractionation demonstration. Just like the previous two, we're treating a fairly highly impacted groundwater with AFFF contamination and looking at the water treatment and PFAS concentration for waste minimization. So in this presentation, I'll go through a very brief overview of the SAF technology, talk about the objectives specific to the demonstration, and then we'll go through the results, mostly focusing on the technical performance for PFAS removal and concentration, a little bit on the economics. I'll share some cost information with you, and then I'll touch on air emissions because that's a common question that we get before jumping to some summary slides. So briefly, I want to talk about the SAF 40, which is really a PFAS water treatment system in a box. So the blue box here is a 40-foot shipping container. And what's happening inside the 40-foot treatment plant is we've got the primary foam fractionation process happening in the 4 large tanks here on the left side. And so water's coming into the feed tank on the left. And in each of those 4 primary fractionation tanks, the air is bubbled up through the tank. And because of the amphiphilic nature of PFAS, where you've got a hydrophobic end and a hydrophilic end, those molecules like to align themselves on an air-water interface like the surface of a bubble. So as you flow air through the system, it pulls the PFAS up to the top of those tanks where a foam is generated that is enriched very highly in PFAS that's collected in the hoods on top of these tanks. You can see the one on the left here. And then that foam is collected all the way over on the right side of the tank. At the end of the primary fractionation, what's left in the tank is treated water that can be discharged. That concentrated foam is collected over on the right-hand side of the vessel. And you're getting about a 5 to 20x concentration factor in the primary stage. Once you've got enough foam from that foam goes into the secondary treatment stage, which is the 2 smaller tanks over here on the right side of the container. And during that secondary fractionation, we get more and more enrichment of the PFAS in the foam and add another 100 to 1000x concentration factor. As that foam is collected in a separate tank over on the right, when enough of that exists to do a tertiary, one of the 2 tanks over here on the right can do a tertiary treatment stage where we'll add another 50 to 200x concentration factor. So, and that's optional. It can be run in that mode or not, but that's how you get the highest concentration factor. So just from a practical standpoint, what that meant in this demonstration was for every 1,000,000 gallons of primary treatment, the SAF generated between 8 and 333 gallons of your concentrated liquid waste for destruction, depending on the conditions that we were operating. So that's the SAF 40. Now, what that looks like at different sites depends on the foaming conditions of that particular water. So different PFAS signatures will drive different treatment approaches and different optimization strategies. So when we look at many groundwaters, for example, they have well above a regulatory standard in terms of PFAS concentrations, but very often not enough PFAS or other constituents to generate a lot of foam. So factors like organic content, salinity, pH, non-target PFAS, all of these things will affect the amount of foam that's produced and the quality of that foam, whether it's wet, dry, stable, unstable. If you have a nice stable foam, you're generally going to have better PFAS separation. That's not required. You can run it in a very low foaming system with what we call bubble fractionation. But in general, you're going to get your best efficiency for PFAS removal with a stable foam. So because of that, we will often use what we call a booster, which is really just a foam enhancing compound. Some of them are surfactants, for example. And if you look on the left-hand side of this, you can see a light foaming groundwater with no booster starts out to produce some foam in the hood, like you see in the top left. As you go through the batch treatment duration, which, for example, is typically between 45 and 55 minutes, halfway through, you're starting to lose some of that foam. By the end, you see very little foam. When you add a booster, you get much more stable foam generated throughout the batch treatment cycle. And even at the very end, there's still some foam there. So that typically is going to be when you're getting your most efficient PFAS separation. So specific to this demonstration, we had really three overarching technical objectives. One, of course, being to demonstrate the SAF for separation and concentration of PFAS. The second being to look at a variety of different factors that can affect performance. So these include the boosters, the post-SAF polishing that we used at this site, and I'll talk a little bit more about that in a second. Variability of temperature, so we're operating over a 7-month time period, ultimately in the field, so we wanted to see how much does that affect performance, and then look at where does that PFAS end up, including looking at potential for air emissions. And then finally, to compare the cost of technical metrics to things like GAC or conventional ion exchange resin. So within that, then, we have a number of performance objectives and very specific objectives to the demonstration. So we wanted to make sure that our system, of course, met the discharge criteria, that we achieved, in fact, a high concentration factor of at least 2000x, and that the overall cost was going to be less than conventional systems. The other two performance objectives, as I mentioned, one was to look at air emissions and to see, number one, was that an issue and how much could that be reduced using vapor GAC? And then lastly, to provide PFAS concentrate to the destruction vendors for the demonstration. And, one thing that we found there is because the factors were so high, we actually had to dilute our concentrate at the end to make sure we had enough volume for the vendors. So this was the overview of the plan view rather, for the demonstration. So the blue rectangle here, sort of in the upper middle, that is the 40-foot shipping container for the SAF on the site. Up above that, you see the two circles. Those are the polishing vessels. So that's two 2,000-pound GAC vessels. And the reason those are used at this site is, number one, we did have fairly high influent PFAS concentrations, essentially identical to what Rhea and Erica showed. 20,000 ppt of PFAS plus or minus, and then about up to 50% more total PFAS than that. And we also had a discharge criterion at Biddle Air National Guard Base, where we were located, where we were discharging to their surface water, stormwater treatment system, that we actually get below the discharge limits for their system in our discharge system. So in order to make sure that was happening while we were changing conditions and running all these different boosters on site, we wanted to make sure we could meet the requirements. So we had those GAC vessels. So I'll show you results both from SAF alone and from the total system. Down here to the left, you might see this triangle of 3 little green dots. Those are the groundwater extraction wells. So there's a combined flow rate coming out of those of 45 gallons per minute. That goes up into a manifold and into the influent for the SAF system. These are some photos to show that. Again, 45 GPM coming in. In the top right photo, you see the actual SAF sitting on the site. In the lower left, the two cylindrical tanks are the GAC polishing vessels. There's also a surge tank there so that we can regulate the flow going through that polishing stage. The groundwater wells are in the bottom middle photo out in that nice grass field, and then you can see the little extraction well manifold. So that provided continuous treatment at about 45 GPM throughout the demonstration. For the boosters, we wanted to look at 2 different types of boosters, specifically bio-derived boosters, so bio-derived molecules that have some biodegradability and are also low toxicity. And then we are comparing that to chemically derived boosters, that one in particular, that is less biodegradable for sure and has slightly higher toxicity, but is much better at removing some of the short chain molecules. So there's a trade-off with some of these compounds. The chemically synthesized booster, number 400 here, and I'll get into what that is in a second, does have that property for higher short chain removal because it's cationic. So you're getting an ionic interaction with your PFAS molecules. So while we did not necessarily set out to test the SAP with this groundwater without boosters, because our laboratory testing, showed us that was not going to be a very efficient way to treat this water, we did go ahead and run it for a period of time just as a baseline. So again, didn't expect this to get necessarily high removal rates, but wanted to establish that baseline. So I'm going to show you 4 of these slides that look like this. I want to take just a second and explain the slide. So the top bar chart is going to be your percent removal. The purple bar, or the top bar for each constituent, like PFOA here at the top, that top bar is the percent removal from SAF alone. The bar right below it, which is a light blue, is the percent removal from the system after polishing. So you can see that even where we were only getting 68% total target PFAS removal with no booster, 59% total PFAS, we're getting 100% removal with the polishing. And when I get to the cost comparison at the end, just to make sure we're absolutely apples to apples, the cost comparison is the total system, including polishing. So then the bottom chart is showing you the same data, except the actual mass concentration. So it's showing you the influent concentration in the top dark colored bar, and then the effluent concentration from the SAF in the purple bar. And if there was any effluent from the polishing, that would be a third light blue bar. But in most of these, you're not going to see a light blue bar because there is no effluent from the polished system. Now, one interesting thing, when operated with no additive, you do get a very high concentration factor. So we're over 100,000x concentration factor, but you're sacrificing some PFAS removal to get that high concentration factor. So in contrast, when you use booster 100, which is saponin, we're getting still a very high concentration factor, 60,000 to 100,000. However, you're also getting a very high PFAS removal rate. So you can see PFAS and PFOA, it's almost complete removal. But when you get down to the shorter chains, you're giving up a little bit on PFHXS, but PFBS, there's pretty much no removal. So that's with the bioderived boosters, a little bit of the trade-off there. Still total target PFAS removal, 96%, total PFAS 88, so pretty high. But again, definitely giving up something on the short chains if that is an issue at a particular site. Now we go to the chemically derived booster 400, which is cetrimonium chloride, or CTAC. And here is where you get the highest PFAS removal. So again, pretty complete removal of PFOA, a little bit less on PFAS actually than saponin, but your total target PFAS 98%, total PFAS 97%, PFBS almost 100%. So then when you look at the actual mass concentrations, you can start to see, orders of magnitude. So, you're over 2 orders of magnitude for PFOA, almost 2 orders of magnitude for PFAS. Saponin was actually over 2 orders of magnitude. It's about 2.5. So you can start to see that for the different booster compounds. We did test a third booster, booster 600, because it's highly biodegradable, and it had performed well in the laboratory tests. It did not perform as well for us in the field. So we only got about 79% PFAS removal. And we suspect, because this one, under the right conditions, is subject to some spoiling, it does have a shelf life, that's probably what happened here, and the batch just didn't perform like we expected. So here in this demonstration, the results were what we wanted for that particular booster. But I wouldn't necessarily discard it. I think it does have some properties that are attractive, and I think for future we'll continue to look at it. But in this one, clearly SAPN and CTAC perform the best. So looking at the cost analysis, I wanted to give you some real cost numbers. And so what we did here is we looked at the system that was used in the demonstration and said if we scaled it to 100 GPM, because it was operating at about half capacity at 45 GPM, just because that's what the groundwater wells produce. But if you just scale the numbers up to 100 GPM and take the assumed PFAS influent at about 22,000, treat to MCLs, and compare that to a traditional GAC system, what would that look like in terms of costs? And for the GAC costs, we didn't make these up. These numbers came from DoD sites, actual cost numbers for GAC systems performing under similar conditions. And what you can see, very quickly is you're definitely going to have a little bit higher capital cost with a SAF system, but the operational costs are so much less that within about 2 to 3 years, you cross the break-even point. And if you operated a system for 20 years, you're talking about $6 to $7 million less expensive than a GAC system. But in any case, less than half the cost of a GAC system over the remediation timescale. So that's the trade-off with this type of system. I want to touch briefly on the vapor sampling before I wrap up with some concluding slides, because this topic does come up a lot. The question of, are you producing aerosols within the system? And if so, what does that mean in terms of air emissions, either around the treatment system or through the GAC filters that filter the vents on the top of the system? So we sampled within the SAF, we sampled the effluent from the GAC, the influent to the GAC, as well as ambient conditions. And what we saw from that is summarized in this table, at least for a number of different conditions. So we used different types of GAC. We used a mist eliminator within the system. We did it without that. We switched from the small GAC canisters to 255-gallon carbon drums to see if we could completely scrub, anything coming out of it. The real take-home message here is that we saw about 0.0003% to 0.0009% of PFAS going through the system showed up anywhere in an airstream. And when you convert those to concentrations, we're well below any concentrations of concern, whether it's OSHA inside the vessel or any discharge criteria. So we were pretty pleased because this was really, as far as we know, this is the most rigorous sampling and analysis of potential air emissions from a foam fractionation system. So this table is really just a summary of all of the results. And if there's really putting it all on one page, this is the one table that I would take away. The reason there's 2 columns here is it does make a difference if you're running a SAF system at half capacity or so, like this one, or if you run it near capacity, so on the cost side. So when you look at the bottom 2 rows, your 30-year cost savings is actually quite a bit higher if you're running near capacity than at half capacity. So that does factor into this. And then also your operating cost savings go up the closer you are to capacity. But we treated about 4.5 million gallons of water during this demonstration. So if you extrapolate that out to a year, so this is for 1 year, you're more like 7.5 million gallons, just scaling it up. So that table is useful just to think about how many tons of media do you avoid using, and how much cost savings is there. So big conclusions from the demonstration, about 98% total PFAS removal, concentration factors from the high 10s to 100,000 using the optimized booster additives. The MCLs were achieved with no pretreatment. One of the nice things about SAF, it really doesn't care about incoming carbon, TOC, doesn't care about ions or any of those things. There are just some bag filters on the front end to take out the largest particles. So this can be used for very diverse water types, including landfill leachate or other complex industrial wastewaters. We got, of course, very low waste volumes generated. That was validated during this demonstration, which is great for lowering the cost of downstream destruction and logistics. And that's a completely aqueous waste stream that's coming out of SAF. The major benefits really to DoD are summarized on this slide: minimizing waste. Most destruction technologies, if not all, are compatible, and we have worked with almost all of them at this point. And I can answer any questions about that experience. The nice thing about the treatment system in a box is these are very rapidly deployed, and usually you're putting water through it within 2 days of being on site. A pretty significant cost savings over the life cycle of a treatment plant, even at 15 or 20 years for sure. And then finally, meeting discharge requirements. So I will wrap it up there and take some time for questions.
Thank you, Kent. We have time for just a few questions. We're going to start off with one from the University of Utah. Since foam formation correlates with the CMC, how effective is SAF at removing short chain PFAS compared to the longer chain PFAS like PFOA and PFOS, especially at low concentrations?
Yeah, so first one clarifying point. So we're generally not at high enough concentrations to trigger micelle formation. So you're not actually seeing anything above a CMC typically. I will say when we have very high PFAS concentrations, as we did in these groundwaters with something like CTAC, then you do in the foam have the potential to start to form micelles, which is actually why I think the PFAS treatment efficiency is slightly less with CTAC than saponin. Having said that, getting to the question on long chains versus short chains. So, as I mentioned, unless you're using a cationic booster, you're definitely going to see a drop off between somewhere in the C5, 6, 7 range, and that does depend on water type. But if you look at an equivalent KD essentially for these compounds, the break really occurs for carboxylic acids. You're going to see it between PFHXA and one higher than that. For sulfonic acids, you get one more carbon basically. So you're almost always going to do a pretty good job with PFHXS. It will start to drop off as you lose carbon below that. It's a pretty steep drop off from there. So that's you see C6, C5, 6, 7 is where the break is. But with CTAC, you're going all the way down to dropping that down to C4 or C5.
Thank you so much. This next question is from Nafak Exwick. Can you talk about energy demands for SAF and if portable solar or other generators are enough to operate the unit in remote areas for more than a month?
Yeah, so I believe it's a 3-phase 480 volt power is what's needed. I have the spec sheet for that. Off the top of my head, I'm not 100% sure I'm giving you the right number, but I can definitely follow up with the exact electrical requirements. And by the way, in the final report also, we have all of that tabulated, the exact energy usage, kilowatt hours, et cetera.
Thank you, Kent. A number of people have asked about the project number. The project number is on the slide that is shown right now. When will your project report, when do you expect it to be available for download at this website?
Yeah, so the draft report was actually just submitted last week. So it'll take some time, obviously, to go through the review cycle. And I don't want to try to predict that because I don't have control over it. But the draft report is submitted. So like Erica said early on, I think within a couple of months, those will be finalized and available online.
Great. Well, thank you so much, Kent. We are unfortunately out of time. For any questions that remained unanswered, just a reminder that you can go to the SERDP and ESTCP webinar webpage associated with this particular webinar, download the slides, and the contact information for our speakers, both phone and email, is included in the slides should you have any burning questions that we didn't get to today. So I'd like to also remind all of you that you can register for future webinars on the SERDP and ESTCP webinar webpage, which is shown here. And as Andrea mentioned in her introductory remarks, in addition to upcoming webinars that you can register for, you can view archived webinars all the way back to October of 2014. And before we conclude, I'd like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We'd appreciate it if you could take a moment and complete the survey that will pop up on your screen at this time. Thank you again for joining us, and thank you to our wonderful panelists today. We really appreciate your time and commitment to the SERDP and ESTCP webinar series. That concludes today's webcast. Thank you again. Bye-bye.
Thanks, everybody. Bye.